Hey, what's up, guys? This is Sean here. So today, let's take a look at last problem of last week's weekly contest, number 1611, minimum 1-bit operations to make integers zero. Okay, so this is like a quite interesting problem. Okay, given like an integer n, you must transform it into zero using the following operations any number of the times. Return the minimum number of operations to transform into zero. So it means that you're given like a number n here, and you can only perform one of those two operations. So what are those two operations? So the first one is that change the rightmost bit in the binary representation of n. So the zeroth bit means that, let's say if we have 10, 10, 10, 10, 1001, it means that you can only change the the rightmost bit, which is the last bit. You can either change this one from 0 to 1 or from 1 to 0. Okay. So that's the first thing the first operation you can do, which means you can only change the last digit. And the second one is a little bit weird. Basically, if you want to change the ice bit, okay, mm, for example, if you want to change this the leftmost bit here in the binary representation of n here, you can only change it if the I minus one bit is one and the rest is zero. So what does this mean? It means that if you want to change this bit here, you can only change it when the bit is like this 1 1 0 0 0 0. Okay, only then you can change this one from 1 to 0 or from 0 to 1. But for this problem, there's no point of changing this one from 0 to 1 because we're trying to change this n, convert this n into 0. So which means in order to change this the not the non rightmost digit, we have to somehow convert this binary strings into this format. Then we can change this one to 0, right? And then the rest will be will be this one. Okay. So yeah, so that's basically those rules of this problem. Okay. And okay, so in order to do that, right? Let me try to write something here. For example, right? Let's say we have a num we have integer we have a string like 10 11 0 1 1 0. Okay, let's say that's the n here. Let's say n is equal to this one. Okay, and so in order to change this one to 0, so we have to first basically we'll always try to change the leftmost digits from if it is 1, okay? Because that's basically we're trying to use like this kind of greedy approach here. Basically, if the leftmost digit is 1, we'll try to change this one to 0. But in order to change this one to 0, so we need to convert it. We need to do this, right? We need to do something like uh, we need to change this one to what? To a 1 1 0 0 0 0 0. Okay? Basically, we need to change this part to it. Okay? I'm gonna do a comments here, right? So the first step is that we have to somehow change change this strings to 110000 so that we can then change this one to I mean to 0. Okay. So now, so basically from the first step to this step, what do we have here? We have, I mean, we have like somehow, right? We somehow have to change this one. We need to change this one to 100000. Step one, right? Step one is this. Okay. Step one is this. We need to change this one to that. And the second step is what? So the second step is we do a plus one here, because the second step is that we just now we can simply we can use the second operations here, where we add this, where we revert this thing, the one to 0. Okay, so change 1 to 0. And then how about the second step here? So the second step is now we just need to convert. Now the leftmost bits have been changed to 0. Now we just need to change the rest thing into 0. So which means, as you guys can see, before we had like 7 digits. Now we only have 6. That's like a sign of a recursion, right? Basically, now we just need to convert this 10000 to 0. Basically, that's the 3 step uh, to convert that. Okay, and for this part, for the second, so basically, and this one will result to 1, right? And this one, the third step, will result to what? Assuming we have a DFS, then it's going to be a 10000. Okay, right? Because at here we have like at the beginning we have DFS, right? DFS 1011010, right? At the beginning we have that. So now the first step is we is equal to what? Basically, we need somehow, first step, we need to convert this part into 10000. Okay, assuming we have a function here, we have a helper function here to help us convert these things, right, to this one here. And then the next one is we plus 1, because the next step is we revert the leftmost bit. Okay, and then we do the rest is DFS of 1000, and we have 5 zeros. Okay, so that's the that basically that's the DFS. That's the DFS transition function here, right? And now about this helper, because remember, so the DFS, the definition of DFS is the DFS is what's the DFS? The DFS the minimum steps to convert n to 0. Okay, and the helper. So what is the helper? The helper is like helper n, right? So helper n is the minimum steps to convert n to what? N to basically to 10000. Basically the same length of n, but with 1 at the first bit and 0 for the rest bits. Okay. And so we already have like the definition of the DFS. Now we just need to consider how can we implement this helper function, right? Which will be converting this n to this to 10000. Okay. So you mean okay? So now to be able to convert 100 100 to 100 000, so we have to make some observations here, right? So I mean, there are like two cases here. I mean, you guys just need to take a close look. And so the first case is the if basically if the bits, let's say I'm defining a bits here, right? If the bit 0, which means the first bit the bit value is it's 0. Okay, so uh, well, actually, you know what? So I think the one case is easier. Okay, so if the first bit the first bit value is 1, and then we just need to convert the remaining parts into 0. So, and as you guys can see, so this is exactly what the DFS is doing, right? Basically, if the first bit is 1, we can simply do what? We can simply do a 1 plus the DFS and this part, right? So the remaining part, assuming like say this is the that's the case, right? It's gonna be a 1 1, or you know what? Let's do this. 1 XX. So we have 6x here, right? So it's gonna be a uh, let's say there's a s and 5x here, right? So if s is 1, then we have 1 plus DFS x 5x here, because all we need to do is just basically we don't even need the 1 here, because we just need to convert the remaining to 0, and that will give us this 1000. Okay, and the more complicated case is if the s is 0. Okay, so if the s is 0, uh, and we want to basically we want to flip this 0 to 1 so that we can convert these things to 1 and 000. But so again, right, so in order to flip the first bit, in order to flip the first bit, so we have to first convert these things to what? To S1 0 0 0 0, right? So the first step is this. So 2.1. Okay, so the first step is from S this to this, right? Because only when we convert this string to the form of this one, then we can flip this S. Remember, is this a 0 here, right? And then we can flip this one to 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 1 1 0 0 0 0, right? Then we can flip that, and now the remaining part is what? The remaining part is we just need to convert the remaining 10000 to 000, and this is also happens to be the definition of the DFS here, right? So and now we just need to convert these things here, this the remaining part into 0, which happens to be the DFS here. So it's going to be a DFS 1 0 0 0 0. Now we only have 4 zeros here. Okay. So so that's the second part. So the first part, right? So the first part, what is the first part? The first part is we convert these things, the xx to 1 to 10000, what's this? That's the definition of our helper function, right? So basically, so now we have the functions here. So we basically, if the first one is 0, so the first step is that we have to convert this part to 1, 0, 0, 0, 0, which it happens to be our helper function itself. Okay, it's going to be a 5x here, right? And then after that, we flip the first bit, right, to be to convert this 0 to 1. So we plus 1, and then the remaining part is still, right? We still have to now we have 1, 1, 0, 0, 0, 0. Now the rest is just to use this DFS to convert this 1, 0, 0, 0 to 0, so that we will have this final answer, right? It's going to be DFS 1, 0, 0, 0, 0. Yep. So I think now we have already defined these two functions completely, and we can start implementing those two functions. Oh, but remember, so for those DFS, right? Since we also need to use like the memorizations just to save some time, because with the for the DFS for the n and helper ends here, as long as we have defined calculated once, we can simply store the result into a hash table so that it can be reused. So this is something like a DP, right? And now and for the base case, it will be a little bit different in terms of the DFS and helper. So let's take a look at the base case. So for the base case, right? So for the DFS, the base case is just has a one digit, right? So for one digit, if it's zero, what? So for the zero, we don't need to do anything to convert to zero. So which means if there's zero, we simply return zero. So if one, we return one, because to be able to convert one to zero, we just need to we can just simply use the first operations to do it. So which means we will need a one step. Okay. But for the helper here, right? So just be careful when you define the base case for the helper. Remember, the purpose of helper is to convert this n to one, and then uh, follow zeros. Okay, so which means if it's zero, so we need to return one. Why is that? Because now the purpose of the helper is to convert this value into one something. And in case of only one digit, it means that just one without any zero. So which means we can simply use the first rules, the first operations to convert this zero to one. Okay. And if one, then return zero. Basically, it's just opposite, because if it's one, then we have already have the desired format we need here, so that we don't need to do anything. That's why we return zero here. Cool. So I think, yeah, with this kind of definitions, we can start uh, writing the code now, right? So, mm, first, we need a DFS. Okay, we need DFS, and then I'm going to pass in the bits here. Okay, and then we will have like a helper functions here. Okay, so the helper, we also need to define like a bits, because the input is integer, but it's easier for us to convert it into a string format. And then here I'm gonna have like memorizations for DFS. Okay, and also the another memorizations, right, for the helper. Okay, I'll just call it helper here. And here in the end, we simply return the DFS. And oh, sorry. So before doing that, let's try to convert uh, the string, the integer into the bitwise. So the way in Python, we have a function called bin here. So the bin like function basically will give you the return the string here. But the binary will also returns like a string like add 0b at the front. So for example, if there's a 6 here, so we have this one, the binary string is 110, but if you use binaries, I think they added like 0b as a prefix, so it will be like 0b110. But here we only need the remaining part, so that's why I'm going to simply use like a slice of the string here. Basically, we just need to get everything starting from the third character. Okay, so here, yeah, sorry. Now we have the bits. We simply return the bits here. So that's the pre-calculation. We convert this thing to the bits, and then here, right? Now we have this. So first, let's try to write this the memorization part. Basically, if the bits in the memorization DFS, okay, we simply return that. Okay, bits, we simply return it. Okay, and then later on, right? So answer equals to 0, and here I'm going to just copy and paste here. So this is just like a template for the top-down DP, right? And then return answer. Okay, so that's that. And now the base case, right? Since we have already talked about the base case, I think we can simply write the base case here first. Basically, if the bit uh, equals to 0, right? So for the DFS, we are converting everything to 0, so which means here we don't need to do anything, which means we can simply return 0. Or if the bit equals to 1, okay, so in order to convert 1 to 0, we return 1 because we need one step, well, or one operations, okay? Okay, so now I think for the DFS, there's a place we need to be careful because it could be possible that the DF the bits string we pass in, the first one is not 0 because it could be 0 1 1 0 0 1 because later on when we do this like the recursions, even though this bin here at the beginning, this bit will not have like a precede uh has 0 as a prefix, but during the calculations, it's possible that the passed in bits will have it starting with 0 because we will be doing this like a substring later on, right? So if the first one is 0, it means that we don't want to handle the first case. We don't want to handle the zero bit because we're getting the minimum number, which means we just need to start our logic from the first non-zero bit. Okay, so which means if the bit 0 is equal to 0, right? So in this case, we can simply mm, we can do a while loop here, I think, and or we can just use the DFS itself here, right? So we can simply do a DF uh, mm, let's see, we have an answer here. Answer is it's 0. Okay. If the first one is 0, and then we simply do a DFS of the bits 1. Okay. Basically, we just pass this the remaining parts to the answer to the DFS, so that we just ask try to process the remaining parts. Okay. Else, right? Uh, Yeah, else, like I said, so else it's this case, right? We'll need to somehow convert the substring, right, to the 1000, and then plus one, and then do a DFS of this. So basically here we'll do a helper here, right? The helper is what we do a helper bits from this. Okay, that's the first step, and then plus one, and then plus the DFS of so of this, right? So how do we calculate that, right? Basically, we need a one at the beginning, right? So we need a one here plus zeros. So how many zeros? So assuming the length of the bits is is five, basically, if there are like five digits here, I mean here what we want to get is 1000. That's what we're going to pass in here, right? So which means we have one here and how many zeros? Basically, the length of zero is the length of the bits minus two. Okay, so we can do a zero times uh, the length of the bits and then minus two, right? So that's how we get this 1000 here, right? Cool. So yep, I think that's it for this DFS. Okay. Now the helper. So the helper is, I think it's quite similar as the DFS here. I mean, we can somehow copy these things here. I mean, I'll just copy this part here, and then I will try to modify accordingly here. Of course, so now we need to use this thing here, right? So this part, and I also copy this part here. That's as the as our template. Okay. So I'm going to remove this. Okay, replace that. But remember, for the helper, the base case is is reversed, right? When it's zero, we need one. When it's one, we need zero. So that's why we have to reverse this part. Okay. Now again, so now it's the time to implement this part. Remember, in the helpers, we have two cases, right? Same thing. If the bit is one, okay. So if the bit is one, then it means that we simply pass the remaining strings to the DFS. It's this, right? So that's the one case, right? So if it's one, we simply do this. We simply do a answer equals to DFS bits one, right? So that's the one case. And for the zero case, we have this function here. Okay. So else answer equals to like helper, right? Helper bits 10, okay, plus one, and then plus what? Plus the DFS of this part, okay. Actually, it's the same of this part. I will just copy it here because we're also going to do the length of the bits minus two. Yep. So that's the implementation of the helper functions here. And then yeah, and then I think it's ready to run the code here. Okay, so this one accepted. Let's try to submit it. No, what? 3-0. Why I'm returning a 0 here? It should be 2 here. Let me see here. I thought I did everything right here. So we have these things DFS 0011. Oh, here. We didn't assign this thing back to the answer, right? That's why. I think here. Oh, okay, but we did assign here. Weird. Okay. Uh, let's try to test that 3 here. Did we return the answer? Okay. Ah, yeah. Sorry. I why why set the value twice here. Okay, right. Okay, cool. So now this time it's accepted. Let's try to submit it here. This is humiliating. 9 is 6. Okay. 9 is 6, but I'm getting 6, but it should be 14. Okay, so here we have 0, the base case, and this is the bits. Okay, helper bits plus 1 plus DFS 1 0. Okay, helper is the same. We reverse that, and then if it's okay. Yeah, I think because I know since it's always hard to type while you're talking, basically we're trying to check if the first bit is 1, right? And then, yeah, okay, cool. So I think this should pass. All right, finally, cool. So it's finally accepted. Cool. And yeah, I think that's the first solutions here, right? I mean this is a solution that I think it's the regular approach. And in terms of time complexity, since I think let's assuming the length of the bits is n here or the l here, right? So every time when we do a bit here, right, we have DFS and we do DFS. Basically, every time when we will reduce the length of the bits by 1 until we reach the last one. So I would say like the time complexity is something similar like O of L, which L is the length of the the bit string. Okay. So yeah, I think that's the first solution I want to talk about today. I would be talking about another unusual solutions, which is called the gray code. But first, let's try to let's recap this solution a little bit. Basically, for these solutions, I mean the main approach is that we have to be able to utilize those two options, you know, you know, and you have to be able to find out, right? So in order to to change the values of the non other than the rightmost bits, you have to use the second rule. And to use the second rule you have to be able to transfer this original string into something like this, so that you can flip the leftmost bit. Okay, and to do that, first we need helper functions basically to convert uh, the remaining string into a 1000 pattern. Okay, and then we can just recursively call the DFS to help us to convert the remaining, right, for us. And then the next one will be the next one step is just to define the helper functions here. And for the helper functions here, there are like two cases, right? So if the leftmost bit is 1, then it's easy. So now we just need to convert this xxxx to 00000. So that's the definition of the DFS. And and for the 0 case, it's a little bit more complicated, which means that to be able to flip 0 to 1, because that's our goal state, right? Then we will go back to the second rules here. So we have to somehow convert these things to S000 S10000, and then we can flip the first bit to 1, and then the remaining will be will fall back to the DFS, which is to convert this 10000 to 00 to 0, which we can just recursively call the DFS. So hence this is the definition of the helper function. And after that, it's just like a few base case, right, that we need to be careful. And then it's this, right? So for the DFS, we just need to be careful with the leading zeros, which will be skipping in this case. Okay, cool. So now for those who are interested in the second unusual solution, this thing is called gray code. So what is a gray code? I mean, for example, right, let's say we have like this n equals to 6 here, right? I mean, if you watch it closely, you guys can see here. So we have 1, 1, 0. For 1, 1, 0, it converts to 0, 1, 0, okay? And then from 0, 1, 0, it goes to 0, 1, 1, okay? And then it goes to 0, 0, 1. And then in the end, it's 0, 0, 0. Um, if you observe this long enough, you might be able to find out, basically between each of those two adjacent numbers, there's only one digit difference. For example, right? So if for this two, right, the difference is this one. Basically, the zero, the one was changed to 0, and between those two, right? So now the 0 becomes to 1. Same thing for this one. This 1 becomes to 0, and for the last one, this the last digit becomes to 1. Sorry, the last bit digit from 1 uh, to 0. So any two adjacent numbers, the difference there's only one bit difference, and that's exactly the definition of the gray code. So actually there in LeetCode, if I remember correctly, there is like this media level problem ask you to generate like the a list of the gray code given like an integer. So that's exactly what that problem is asking us to do. And it tells you the definition of that. I think it's number 89 or 98. I don't quite remember that. But if you guys interested, you can take a look at that. And so if you can realize this is like a gray code format. Um, so and if you for the for the numbers equals to 3 equals to 3, right? So basically there are three uh, bit digits, and to generate the gray code of n equals to 3, right? So that's going to be what? It's going to be a 0, 0, 0, and then it's a 0, 0, 1, and then 0, 1, 1, 0, 1, 0, and then 1, 1, 0. So the next one is, I think it's a 1. Let's see, what's the next one? So the next one is 1, 1, 1, and then the 1, 0, 1, and the last one is 1, 0, 0. Okay, so that's the one of the gray code for the digit for the bit size length equals to 3. And now you can see that. So now we just need to now the problem comes down to what's the how many uh what's the numbers, right? What's the number that's how many steps we need to convert from the from 0, 0 to this 1, 1, 1, 0. So how many of that? So we have 1, 2, 3, and 4. and 4 is just it happens to be our answer. Okay, cool. So okay, I know you guys still confused at this moment, so let me comment out this algorithm here. And then so I think first, in order to use that the gray code solutions, you guys need to know what's the how did we calculate that? Basically, you know, the to calculate the gray code, right? The gray code is the we do a I in range of the uh, divided by n, right? So and then the answer is this. The answer is like, for example, we have a list here. So the gray code is answer dot append the what is that? The I uh, x or the I moved by by one. So that basically that's how the how we calculate the gray code. So why is that, right? And okay, so first we have 0, 0, right? I mean, uh, 0, we have 0, 0, 0, do a right shift by 1 is also 0. So 0 or 0 equals to what? Equals to 0. Okay, right? So that's our first gray code. And now the I equals to 1 here, right? So the 1 or what? So the 1 moved by right shift by 1 is also 0. Okay, but with the XOR here, now we have 1 here. So this is like 0, 0, 0. Now we have 1, which is 0, 0, 1. So now we have 2 here. Okay, so now I is equal to 2, which means it's the 1, 0 and do a XOR with the what? With the so 1, 0, we do a right move, a right shift, it's gonna become to 0, 1, right? So with this, do it with XOR, we have 0, 1, 1, okay? And so on and so forth, right? Now we have 3 here. So 3, I equals to 3 is this, is 1, 1 and 1, right? We do a, so 1 and 1, we do a right shift by 1, it's gonna be uh, it's also a 0, 1, okay, right? And now 1, 1 do a XOR with 0, 1, we have uh, let's see what we have. We have 0, 1, 0. Okay. Now the next one is what? We have so now the I equals to 4, right? So 4 is this. 4 is the 1, 0, 0, right? Do XOR. So this one moved by 1 is 0, 1, 0. So what do we have here? We have a 1, 1, 0. And this is the answers we need here, right? So it happens to be 6. Okay, I'm just doing this, just trying to show you guys how do we calculate this gray code, right? And that's basically the formula of calculating the gray code. And if you guys watch closely, now we have a, what do we have here? We have this 6 here, right? So the 6, it happens to be the 1, 1, 0. And what's the answer here? So what's the values we're looking for here? Basically, we're looking for the I here because um, because I is the times, right? It's the time that we got converted, right? We got converted. How many times is got converted to this one to 6 here? That happens to be our answer, right? Because the you know the I represents the times, right? The times we how many steps we have taken from 0 to this 110. That's exactly what we need because at this moment, right? So the I is equal to 4, right? So it means that because see the I is the index. I is the index to get to the current state, and that's the so basically, when I equals to 4, we get by doing this I do a XOR with I shift by right to right by 1, we get 4. We get this 110. So now the problem comes down to the uh, if you want with this given like uh 110 here, how can we get the I here? Where I with this formula, okay? Mm, so how do we do that, right? I mean, we can do a simple check here, right? Basically, if we draw it closely, basically this is 110, and so with I and I right shift by 1. Let's say we have a hmm, we have A B C D E and F, and this is I. Okay, this is I, and so I shift by 1. What do we have? We have 0 A B C D and E, right? So so this is 0. Okay, this is the I shift by 1 here, and here we have it doesn't really matter. Let's say we have 1 0 uh 1 0 0 1. Okay, and with this and basically this is going to be our n here, right? So with n here and with this formula, can we get I here? We can, right? So because uh let's take a look. So with 1 here, and remember we're doing like an OR here. Okay, we're doing like an XOR here. So when we do an XOR, so to be able to get 1 here, so we only get 1 when these two numbers are different. And with the first one equal to 0, it means that A has to be 1. Okay, and when A equals to 1 here, right, and A is 1, A is also 1, we have 0. 0 means same. When the numbers are the same, then we have 0, which means B is also 1. And when B is 1, we have 1 here. It means that C and B has to be different. Now the C is 0, so on and so forth. We have 0. Okay, so with 0, it means that there has to be the same. So D is also 0, and with D equals to 0, we have 0 here, and E is also 0. Okay, and with E equals to 0, and we have 1 here. So we have 1 do a XOR, then we have 1 here. So the final answer is basically 110001, and that's going to be our I here. Okay, so that's that. Okay, cool. So now the problem comes down, how can we calculate that, right? So as you guys can see, all we need is just like a last digit to record what was the last digit, and then we just with based on the current digit, the nth current digit, if it's 1 or 0, we have a different logic here. Okay, so what I mean by that is this. Okay, I'm going to comment out these things here. So for your guys' reference. So uh, we have answer equals to 0, right? And then of course we have a bits. Yeah, we still need the bits here. Okay, so we have a bits here. Now, like I said, we need the last bit, right? To tell us the what was the last one. And at the beginning, if you guys remember, we had like 0 at the beginning, right? So because at the beginning we have a B, C, D here, right? And there's a B, C. So at the beginning, the last digit is this one, right? Which is 0. Okay. So and cool. So we have for I and bit, right? In enumerate enumerate bits. Okay, so and since we're going to check to flip it, right? And I'm going to convert this bit to its integer format first, because remember, so now the bit is a string here. So the reason I'm doing it is because I'll be checking that, right? So here, okay, 1010. Okay, so it means that, okay, so now we're at this bit here, right? So if the bit is equal to 1, so what does it means that, it means that uh, the the answer we're looking for here has to be different as the last digit. Okay, in this case, it needs to be 1, right? So which means that, let's say we have a current bit, right? We have current bit, it means that it has to be been the opposite of the last bit, which means if the last bit is 0, this one will be 1. If it's 1, and then this one will be 0. So to do that, we simply do a XOR with 1. That's how we convert, basically how we flip the numbers of the last bit. Okay, so that's that. And else means if the bit is 0 in this case. If it's 0, it means that uh, our this our current bit has to be the same as the last bit. Okay, so current bit equals the last bit. Okay, now we have the last bit. Now we just need to do an answer here, right? So we have, um, since we're calculating these things from left to right, so in order to do that, right, we just need to do a answer, uh, do a left shift by 1, and then we plus our current bit. Okay, that's how we calculate, because at the beginning we have 1 here, right? And then let's say, for example, let's say the second bit is also 1 here. So what's the total number of this? So we have to move this left, move this the previously answered to the left by 1, so that we can have a position for the current bit. That's what we're doing here. And here, if we have a 0 here, right? I mean, we have to move the previously answered back left to left by 1, so that we can add this one. Cool. And yeah, don't forget to update the last bit here with the current bit. Okay, and in the end, we simply return the answer, right? Like I said, that's the answer is the I here. Cool. Let's try to run the code here. Accept it. Submit. Yeah, as you guys can see, this one is faster, because I think for this one the time complexity is just it's 01, right? Because the for the bits, the length of bits is fixed. I think it's within the range of 32. That's why this one is much faster. Cool. Yeah, I think that's pretty much everything I want to talk about for this problem. Yeah, if you guys still have some questions, just leave a comment. I'll try my best to explain to answer it. And otherwise, yeah, I think thank you so much for watching this video. I know it's a long video. Thank you so much. And stay tuned. I'll be seeing you guys soon. Bye bye.